Our next speaker is Professor Zhao from Department of Chemical and Biomolecular Engineering, NUS. He's an expert in the MOF and COF materials for separation applications. Today, his talk is MOF-based swing adsorption cycles for wet CO2 capture. Professor Zhao, your time.
Thank you, Prof, for a nice introduction. Can you see my slide?
Yes.
Okay, excellent. So I need to modify the content a little bit just to include more research results. So the title would be the CO2 capture in framework materials from NUS Chemical and Biomolecular Engineering. So I don't think I need to emphasize too much on the importance of the CO2 capture. We're living we are living in a chaotic time. Our daily life has been, deeply affected by the COVID. But let's say 1 or 2 years later, once we have overcome the COVID, next, which I think is more, a bigger balance would be the climate change. So we must do something for example, CO2 capture. And these are some of the available carbon capture technologies. Professor Zhao has mentioned the chemical looping, and he has mentioned some adsorbent materials, which is our focus. So we are primarily interested in adsorption-based CO2 capture. So basically in this process, we have the porous adsorbent materials. And once you have the flue gas come in contact with the porous materials, the CO2 in the flue gas will be preferentially adsorbed onto the wall of the adsorbent materials because of, for example, the van der Waals interactions. And that interaction is stronger between CO2 and the adsorbent compared to, say, nitrogen and adsorbent. Of course, this process is it's more complicated in a real situation because in the real flue gas, besides CO2 and nitrogen, we have other components, for example, water, SOx, and NOx. So that means the adsorbent material should be able to capture CO2 in the presence of moisture and be stable towards acidic gases. So that will be a big challenge for the development of the adsorbent materials. And the key in the adsorption-based CO2 capture is the development of adsorbent materials. And the first type of materials I want to introduce is called metal organic frameworks. It's a type of hybrid organic, inorganic porous materials. And here I give you the history of the development of MOFs along with the BET surface area. So you can see for the conventional porous materials, the surface areas are barely more than 2,000 square meter per gram. But for MOFs, I think the current record holder is already more than 10,000 square meter per gram. So they are by far the most porous materials found nowadays. And because of the rich chemical tunability and well-defined pore size and shape, they've been proposed as a promising adsorbent materials for carbon capture. So far, there are there are hundreds of thousands of MOFs that have been reported nowadays. The next question we want to ask is what would be the most suitable materials that we can scale up and we can test under the real situation for CO2 capture. So there are several criteria that we need to, the material needs to meet in order to be studied under the process scale. The material should have good performance, right? Good performance, I mean high CO2 capture capacity and high CO2 over nitrogen selectivity. And ideally, such performance should not be affected too much in the presence of moisture, okay? Because the flue gas is saturated with water. And the material should be easily available, and it should be easy to scale up, and with a low cost that can be scaled up, okay? So by looking in the literature, one MOF that often comes into our mind is called UTSA 16. This is a MOF that has been reported, by 2012. And they claim that this MOF has a very good CO2 capture performance. And since then, several groups of process engineers, they have done process simulation, they found that these MOF shows at least comparable, even better performance compared to the industrial benchmark adsorbent materials, such as zeolite 13X. So if you look at this MOF, the structure-wise, this MOF is composed of the organic ligand is citric acid. Citric acid is very cheap. It's been widely used as food additive and has been produced many tons every year. So the cost of the starting material is very low. And the performance, if you look at, this is the vacuum swing adsorption based performance. This is regeneration temperature, and this is the cost of the CO2 capture. So you can see these are the projected cost to capture for zeolite, and these are for UTS-16. So you can see that in principle, this material can be a very interesting adsorbent for CO2 capture. However, the original UTS-16 was reported with cobalt as the metal component. And the cobalt is relatively expensive, and the synthesis process is very slow, can be days and even 2 weeks. So in our group, we identified the UTS-16. The next question we want to answer is, how can we make this material more affordable for large-scale application? So by analyzing the chemical structure, we found that actually there are 2 coordination geometries of the metal in the framework. One is octahedral, one is tetrahedral. And we found that actually the tetrahedral building unit, that is a rate limiting factor. That is the reason for the slow reaction kinetics of this material. So by replacing the cobalt with zinc, zinc is famous for the tetrahedral coordination geometry. We found that actually we can make this material in a much faster way, okay? And shown here, these are the photos of how this material look like. X indicate the ratio of zinc in this material. X equals 0 means the pure cobalt, and X equals 1 means pure zinc. You can see that we can gradually increase the content of zinc. And this is a powder XRD of the material synthesized under different temperatures. So this is a X equals 0, that means the pure cobalt. You can see that for pure cobalt, we cannot obtain any crystalline product until we increase the reaction temperature to about 100 degrees C, okay? However, if we start to dope the material with zinc, even at room temperature, we start to obtain some crystalline material, okay? That is because of the facilitated formation kinetics aided by the introduction of zinc. So to make it simple, with zinc, we can make the material faster, milder, and cheaper, because zinc is a cheaper salt than cobalt. So after obtaining the material, the recipe that is ready for the large scale production, the next question is, how are we going to apply that in the real scenario? In the real carbon capture process, if you're talking about adsorption, we mainly have 2 approaches. One is a vacuum swing adsorption. So in vacuum swing adsorption, this is a column. So we'll fill the column with adsorbent materials, and we will introduce the feed gas towards the one end of the column, and the feed gas will travel along the column. And when it travel, let's say if the feed gas contains only CO2 and nitrogen, CO2 has a strong interaction with the adsorbent materials packed inside the column. So you can imagine CO2 will travel slower, and the nitrogen will travel faster, okay? So at the other end, you will collect a light product, which is nitrogen. And then the column will be saturated with CO2. And then you pull vacuum on the other end to collect the heavy product, which is CO2, okay? And once you fully regenerate, the column is ready for the next cycle. So that is just one column. By parallel running this operation with 4 or 6 columns, you can make the process a continuous process. So that is what we call vacuum swing adsorption. This operation works well for dry flue gas, which means if you only have CO2 and nitrogen, it works fantastic. However, in the presence of moisture, you have a different result. Shown here, these are the water isotherm of UTS-16. So you can see that this is the pressure and this is the amount of water vapor being absorbed, you can see that this material actually is quite hydrophilic. At 40 degrees C, you can see a very rapid absorption of water. So once water gets absorbed in the material, the water will occupy the limited absorption site for CO2. So that will reduce the CO2 uptake capacity. Okay, and this is a simulation that we have done on the column filled with UTS-16, just to give you an idea. So this represents the dimensionless length of the column. So here you can treat this point as a feed inlet. This is the outlet of the column. And this y-axis represents the absorbed amount of water. Okay, so for example, let's say this PL, L means low pressure. That means the pressure we used to pull vacuum. Okay, so normally during the operation, we will introduce the feed gas into the column, and then we will saturate the column with CO2, and then we'll pull vacuum. And in this case, if we apply this amount of pressure as a vacuum, after 10 cycles of adsorption and desorption, this would be the concentration of the residual water inside the column. You can see that water start to accumulate inside the column after 10 rounds of cycles. After 100 round cycles, the water front will propagate along the column. After 500 cycles, the column is almost saturated with water. Under the cyclic state equilibrium, CSN is cyclic state equilibrium. Under this equilibrium, the whole column will be fully saturated with water. So that means although the water travels slowest compared to nitrogen and CO2, but after certain numbers of cycles, adsorption, desorption, the column will be eventually saturated with water. That means the column is dead for CO2 capture. Okay, and if you have the vacuum level that is not as good as 0.01 bar, for example, 0.01 bar, it will take sooner to saturate the column with water. Okay, and remember in industry, the vacuum level would be roughly 0.1 bar. Okay, so that means if for this material under the operation of vacuum swing absorption in the presence of moisture, the column will eventually be saturated with water, and the whole column is to be regenerated to remove the water before any further CO2 capture operation. So in short, vacuum swing absorption will not work for wet condition. However, that doesn't mean that's the end of the story. If you look at the isotherm of CO2 under different temperatures, you can observe that this water uptake has a strong correlation with the temperature. Let's say if you run this water absorption at 40 degrees C, you have this very steep isotherm. But if you run at 120 degrees C, you have a much flatter isotherm. That indicates that we can use another swing called temperature swing to remove the absorbed water and make this process sustainable even in the presence of moisture. Okay, so temperature swing compared to vacuum swing. So here in the vacuum swing, we will pull vacuum. In the temperature swing, we'll just increase the temperature, okay? Because the absorption process is exothermic process, which means it is unfavorable at high temperature. So if you increase the system temperature, you will trigger the desorption, and that will remove both the absorbed CO2 and water. So we want to answer the question, can we use temperature swing absorption to fully regenerate the absorbed water and make this process a successful one in the presence of moisture? We've run some simulation. This is the result. So basically, this is the amount of component being absorbed. This is the axial position. You can treat this as the vertical position of the column. So this is the inlet position. This is the outlet position. Okay, we've run many rounds of cycles until we reach the equilibrium state of cyclic steady state, and we found that actually the column, although we cannot completely remove the water, but under some conditions, the water will only accumulate at the entry part of the column. That means the majority of the column is still dry and water-free, okay? So the biggest take-home message is with this temperature swing, we can successfully regenerate our adsorbent, even in the presence of moisture. And we've done some performance benchmark. We found that, for example, this is a feet of water content, and this is the productivity of carbon capture per unit amount of adsorbent. And this, the red one indicates zeolite under the feed temperature of 30 degrees C and the regeneration temperature of 167 degrees C. And the blue one is UTS 16. So you can see that under similar conditions, the productivity of our material is higher than zeolite. And then if you look at the recovery and purity target, that's a target set by US DOE, which means for CO2 capture, we need to reach a 90% recovery, and capture CO2 should reach a purity of 95. And we can see that under certain conditions, we can successfully meet those targets, okay? So the separation is feasible even with the CO2 concentration as low as 5%.
Professor Zhao Dan, you may need to wrap up in 1 minute.
No problem. Another story is a COFs, covalent organic frameworks, and they are pure polymers. They do not have metals, and these are the COFs synthesized in our lab. And we have finished one work to systematically evaluate the COFs. We've chosen 6 COFs with different pore size and different geometry, 2D stacked and 3D interplanetary structures. And we've measured the water, we've measured the CO2 uptake and the heat absorption and selectivity and water absorption. We found that compared to MOFs, one feature, one take-home message I want to share is COFs are hydrophobic. Okay, you can see from this S-shaped water uptake. And you may wonder why this S-shape is interesting. Oh, by the way, we test the stability. They are very stable in water. We run a COF in a breakthrough. We saturate column with different level of relative humidity. And we found that actually under certain level of humidity, the carbon capture performance can be retained. So that means because of the hydrophobicity, this material can be used for a certain level of wet CO2 capture. All right, that's all I have. Thank you very much. Thank you, the support from Energy Center and ExxonMobil. I'll be glad to take your questions.
Thank you, Prof. Zhao Dan, for your nice talk.